exponential models based on percent growth. So it says that there are many examples of growth in the real world that occur at a constant percent rate. Okay? That constant percent rate that rings true to me is when you're talking about any type of banking. Okay, your percentage rates for a savings account, maybe if you have a percentage rate for a checking account, your mortgage on your house, that kind of thing. A lot of it relies on money. So this phenomenon gives rise to exponential functions. So let's take a look at this first example, which I should have thought of because during the summer and the fall when you've got a lot of fruit in your house, you probably see a lot of fruit flies. So it says a population of fruit flies is growing at a constant rate of 6% per hour. The population starts at t equals 0, okay, that's our time, with 28 flies. Okay, so this is our starting point. And this right here is going to be our growth. Okay, our growth rate. And then this back here I said was our time. So it says using what we learned in the last lesson. I did skip the last lesson because it was on percents, and you guys have done enough percents in the past. Determine the population after each of the following amounts of time. Show the calculation you use as repeated multiplication. So let's just sit and think for just a second here, okay, about your percents. So for exponential growth, it's going to look something like this. Y equals your initial amount, I'm going to call it A, that's what you start with. And then it's going to be 1 plus your rate, and that 1 is that 100%. 1 plus your rate in terms of a decimal raised to some time t. A is your initial amount times 1 plus your rate, and that rate has to be expressed as a decimal, plus that 100% raised to the time t, okay, or your t power. So at 1 hour, how many fruit flies are there? So we started out, okay, our initial amount was 28 fruit flies. And then we know that they're growing. We're growing at a constant rate of 6% per hour. So we take and we add, we say 1 plus, well, what is 6% as a decimal? 6% is 0.06 as a decimal, 0.06. And then what is our time? Our time is 1, okay, 1 hour. So if we go to our calculator and do that calculation, we get approximately, now you're going to get a decimal, but we're not going to have part of a fruit fly. Okay? So we're going to say approximately 30 fruit flies. So then repeat that process. And what about at 2 hours? So now sit and think to yourself, I'm not going to show this as this repeated multiplication. I'm going to keep continuing using this formula. So if we started out with 28 fruit flies, they're still growing at that constant rate, but now what is my time changed to? My time is now 2 hours have passed. So how many fruit flies do we end up with after 2 hours? Okay. We've got approximately 31 fruit flies. And then after 3 hours, continue on. How many did we start with? Okay, 1 plus that constant growth rate and raised to the 3 hours. Okay, that's 6%. We're not getting a huge amount of growth per hour, but still, okay, and now we're at 33 fruit flies per hour. So they're increasing slowly, but still, okay, over an hour, if you've got 33 fruit flies in your house, that's going to make you kind of crazy. So part B, it says, based on A, find a formula that models the population P. Well, we already did that because I was too excited to kind of walk us through that. But we'll change what we use to P's and T's. Okay, So the population P of T as our time is equal to, what did we start with? There's our initial amount. And then what was our growth? It was 1.06. Now some of you might be saying, well, where did you come up with that 1.06? Well, I just simplified, right, that that's in parentheses. And that's raised to our time T. So that's in general, we could find out our fruit fly population at any time. So now they're asking, what is the value of P of 24? So a full day later, okay, after 24 hours, how many fruit flies do I have in my house? So P of 24, so 24 hours. Take a minute if you want, if you'd like, go to your calculator, okay, you can pause the video and type that in. You should end up with 113 fruit flies. All right, so part D says, what does the calculation you made in C represent about the fly population? And then it says, state the range of the population function over the domain interval from 0 to 24. So that's your time. So that calculation tells you that you've got 113 fruit flies. It's making you a little crazy right now. Okay? Over that 24-hour period, so within one day. So what's the range? Okay, so we know our domain is our time. Our range is then the number of fruit flies. We'll call it F squared. It's fruit flies. Little math humor there. All right. So what is our range? How many did we start with? So I had my live audience in here for the first part of that lesson, so I forgot to give them a shout out. So that is my Boston class. Bunch of rock stars in that Boston class. Nice job. Marine Corps, maybe someday you might be lucky to be the live audience as well. All right, so let's continue on with our fruit flies. So our range, we started with 28 fruit flies, okay, which is less than or equal to that population, which is less than or equal to, and how many did we end up with in the end? 113, okay? So if we go and we take our equation back up here, okay, that we wrote in B, and if we were to graph that, it says use your calculator, sketch a graph of this function over the interval from 0 to 24 hours, okay, and from 0 to 120. So essentially on our graph, we're going from 0 to 24 hours, and then from 0 to, they just rounded it and said 120, because we know we do end at 113 fruit flies after 24 hours. So where do we start? Okay, we start at 28. That's our y-intercept. Okay, that's our beginning point. And then it increases, okay, exponentially. And then we end, I went up a little too high, okay, to where, whoops. So let's back that up just a little bit. Okay. So that point right there would be 24, 113. Okay? So now we've got a multiple choice question. It says exponential growth is fairly easy to model and fairly easy to interpret, meaning to understand what they're asking. So it says consider the following. If the savings in a bank account can be modeled by the function, okay, here's our function, which of the following is true? Okay, so this is our, okay, what I talked about in the beginning, that's our initial amount. Okay, so that's what we walked into the bank with, okay, when we wanted to open up our savings account. And then, right, we've got 1.045, okay, is our growth rate. So what is the percentage that the bank is paying you for them to keep your money? Okay, so that 0.045, remember, that's been added to that 100%. So what is this decimal 0.045 in terms of a percent is 4.5%. Okay, so then scanning those choices, okay, and then obviously that T is the time. So we end up with choice 3. Started with 250 and the interest rate is 4.5%. Go ahead and flip the page. It says we should also be able to model exponential decreasing phenomena based on what we learned in the last lesson about percent decrease. So remember to always model based on the percent that remains. Okay, so now we're just gonna flip our idea around. Instead of increasing, we're going to decreasing. So we're talking about as water drains out of the pool, the depth of the water decreases at a constant percent rate. Okay, well there's our percentage per hour. The depth of the water when the draining begins, okay, so there's our starting amount, is 12 feet. So just like we did in number 1, find the depth of the water in the pool after each of the following time t. So I'm going to go right to our equation again. So if we sit and think about this, okay, so this is decay, okay, it's decreasing. So our decay, our exponential decay, going to look like this in general. Y equals still our initial amount, but now what's happening each time, okay? That amount is going down, it's decreasing. So we're going to take our 100% and we're going to take away, okay, our rate, that amount each time raised to the time t. Okay, so that 1 minus r is the percent that remains. Right? So the only difference is their subtraction because we're decreasing. So let's look. So after 1 hour, so the depth of our water, we initially started with 12 feet, and then we're decreasing. Okay, we're decreasing 1 minus, okay? What is our percent rate that we're decreasing by? Our percentage, okay, is 20%, but what is 20% as a decimal? Okay, it's 0.2. So this always has to be represented as a decimal. So 0.2, and then raised to the 1 hour. Again, doing that calculation, by all means use your calculator. We're going to be at 9.6 feet. And 12 times 1 minus 0.2, but now we're changing the time because now we're at 2 hours. And that's 7.68 feet is left in the pool. And then, we're talking about pool. Then after 3 hours, our initial amount, 1 minus 0.2 raised to the 3 hours, and that gets me to 6.144 feet left in the pool. Okay, so it says based on A, create an equation that gives the depth d of the water of the pool as a function of the time in t hours as it has been draining. So our depth d of time t is equal to our initial amount, okay, which was 12. And then if I were to take it, again, I wrote all this out, if I were to take and simplify what's inside those parentheses, 1 minus 0.2, I'm pretty sure you guys are cool with 0.8. Okay. And it's raised to the time t. So that's our formula that I bet as we get down further, they're probably going to ask us to sketch it maybe or use it, okay, for any time to see what the depth of the pool is. So, oh, look at that. Using your calculator, sketch a graph of the function over the interval from 0 to 20 hours. So almost a full day letting this pool drain. So 0 to 20 hours. And the depth from 0 to 15 feet. Now, obviously, the pool only had 12 feet in it, so they just kind of rounded that and said 15. So where does the pool start? Okay. The depth of the pool, okay, starts at 12, so that's our y-intercept. And then what is it doing, okay, as we continue on with time? The depth is decreasing, okay? Oops, that didn't come out very exact. I think my smart board's a little off. Okay? And eventually that would empty, okay? So it's safe to cover a pool after it reaches a depth of 1 foot or less. What is the minimum number of whole hours that we should wait to cover the pool? Explain how you found your answer. So I'm going to pause for a second so I can bring up my calculator so we can look at the table. Okay, so right now I'm on a graphing page and I'm going to type in my function that we came up with in B. So 12 times 0.8 raised to the, now the calculator only understands x's and y's, so don't raise it to the t and wonder why it's not going to work. It's got to raise it, whoops, we got to raise it to the x power. Okay, enter. All right, and I'm just going to grab my graph and so I can see, okay, a better picture of it. We set ours up to 15, so by all means, okay, shift that around if you'd like. Okay, so you can see that. And I think we brought that out to 20 hours. See if I can, oh, there we go, 20, there we go. Okay, so there's a nice little sketch of it. So now they said it's safe to close the pool when the depth of the water is 1 foot or less. So I'm going to go to my table. So I'm going to do Control T, okay, and go to my table. And, okay, let's look here. So now remember, this is what is drained. Okay, so at time 0, we have 12 feet in the pool. Time 1, or excuse me, t equals 1 hour, we got 9.6 and then 7.68. Okay, we did those calculations in part A. We've got to find, okay, still at 5 hours, we've got almost 4 feet left. Okay, keep scrolling through, and okay, we're getting there. But at 11 hours, we're still over 1 foot, so it's going to take us a full 12 hours to get to a safe amount where we can close the pool. Okay, so you could draw yourself that a nice little table. What is the minimum number of whole hours? Explain how you found your answer. Okay, so you could say, okay, using the calculator table, we noticed at t equals 12 hours, the depth was below, okay, 1 foot, okay, or just below 1 foot, okay? All right, it says, which of the following equations would model an exponential quantity that begins at a level of 16, okay, so begins at 16 and decreases at a constant rate of that. Okay, so 16, 16, 16, 16. Ooh, what do we got going on here? In number 2, we got a crazy plus sign in there. Immediately get that one out of there. Okay, number 3, so it's decreasing. So what's happening inside that growth rate? It's 1 minus, and 8% as a decimal is 0.08. Okay, so then what is that growth rate? It's going to be your 0.92. So that one's growth. Okay, randomly minus 7. That doesn't make any sense. There we are, winner, chicken dinner. Okay, and let's go to this last one. We started out with that savings account, and that's our interest, and that as a decimal is 0.035. How much should it be worth after 10 years? So now they're asking us to actually do something, not just recognize the equation. So what are we going to have? We're starting out with 350, and okay, Obviously, you're placing it in a savings account, and it's growing at 3.5% per year. So this is going to be 1.035. You're adding that to your 100%, and our time is 10 years. So go ahead, use your calculator to find that it's number 4.